Hi everybody, so this tutorial would be about capacitors, and I want you to listen a little bit to what capacitors are. I'm going to play a little bit and let me know if something changed. Versus Okay, so what we actually heard right now was me changing the capacitance while playing. And this is not something in particular only to guitar players. Also for DJs and other instruments and every electronic music that you hear, that's what the people actually do. So let me explain to you exactly what have I done, and this also gonna be our first question. So I play some note in the guitar, and this note go through the wire. This electrical information went into my pedal board. Okay, so the pedal board have a button that I can press with my leg. That's what I did here. I just press the button and change the arrangement of the capacitor that I had. So the sound entered this device and sound a little bit differently. Let's call it note style. Okay, and then it went into the amplifier, and the amplifier also have a lot of capacitors. So eventually you heard the sound note star star, let's say. Okay, so that's what we actually doing with capacitor. We can change the information. So this is going to be our first question. So let's start playing with that. Okay, so I want to ask you, what is the equivalent capacitor, okay, of this pedal, okay, of this guitar effect? What do I mean by say equivalent capacitor? All these capacitors, okay, actually can be replaced by one capacitor that's gonna do the same results, gonna give us the same note star that we're talking about. And if you note here that I have two places to connect the wire, and this changing by me pressing the button. So when I press it, it's actually shift from state 2 or state 1. So let's find C total. C is the capacitance, yeah, of configuration 1. This is our first question. What is the configuration when the amplifier connected to place 1? Right? This is going to be kind of some connection here. Okay? Great. So the first thing we need to do is actually draw the circuit in this state. So let's do it. So we have a conductor that comes along and see the capacitor C1. What is a capacitor? It's just a conductor with separation of non-conductor material. For example, air is not a conductor, and another plate of conductor. And I continue, and then I see something really interesting. The electrical current can actually choose where to go, that direction or that direction. This is called junction. And I love to emphasize it by doing a strong. Yes, so one option is going to C2, right? One capacitor. And the other option is going through C3, right? This is the two options. And then I come along after C2, after C3, I see C5, right? Capacitance 5. And then what here I have? Help me? What this is a junction. Perfect. So here I have some junction. Okay? Note, do it like this. Note that, note that after C2, this is not a junction. Why so? You see that we connected to 1, so all the current would not enter this because there's no change in potential between point 2 and this point. Think about as electricity as a water, okay? So if I have change in height, so water would go with the change in height, okay? So this is a mountain, okay? It's not gonna enter here, but it's gonna fall down here. So here there's no two options, there's only one, which is C4. And after C4, I do have a junction. I can choose C5 or C6, right? So it's recombined with that junction, right, to C5. And here The other side is C6, and here I'm out. In pedal board, usually this is called inlet, and this is called outlet. In guitar world, but doesn't really interesting here. Okay? Question?
Does it make a difference if we have the capacitors on the on different sides or in the same one, because they're gonna be in
this thing, you see this corner? This is a conductor. It doesn't matter. It could look in the real life. You see my cable? You see the shape of the cable? It doesn't matter how it is. It just connect here and connect there. For simplification, we're just drawing it linearly, so it's going to look smooth. So I can change and rearrange it the way I want. It's not going to affect the properties of the circuit, because we assume this line doesn't gain any voltage. Okay, it's an assumption. Good. So right now, before finding the total capacitance, I can work out what are the equivalent capacitor. For example, these two. What is the equivalent capacitor for these two? So these two capacitors actually connected in series, one after another. So the formula, when you calculate it in series, it's equal to sum all the opposite of the capacitor that you have, and to correct the unit, just do -1. Okay? So this is when you have in series capacitors. So let's call this capacitor 2,4 to know its origin, and this one, you see clearly in the camera? Good. And this one equal to what? To sum up 1 over C2 plus 1 over C4, and don't forget to correct the units. -1. Perfect. And I want you to note also that what we have here, the same concept, different capacitors. So we have here C35, right, which is 1 over C3 plus 1 over C5 to the -1. Perfect. Got it. And this ends up, okay, this ends up to be, we can rearrange it and calculate it. Usually this here is some numbers, you put it in the calculator and find it out. But now I have a new capacitor, a new circuit. I want you to see it. So right now, if I'm going to plug these two inside, I'm going to have this circuit. And this is the same circuit. This is C1. And then I have a junction, right? And I see these two capacitors. This is C6. This is C1, but here I got C35 and C24. You see it? And what's common to these two capacitors, that they have the same difference of potential. This is called connection in parallel. Okay? So I like to do it that way, for example, series, and parallel I do that way, which mean parallels. Sorry? Parallels. When they share the same voltage. Here when they actually fighting on the voltage. Each one of them want to take some of the voltage to himself. Here they're going to share it. They're between the same mountains of voltage, of potential, of energy. Yes? So this one is really simple. It just sum them up. Okay? This is really easy. So what is the result of these two? What is the equivalent of mega C2, 3, 4, 5? Exactly, simple as that. Okay, so this is a more easy way. And I want you to notice that the capacitance, when you plug it in a parallel, what's happened to the capacitance is actually increasing, right? You see it? You see it? And what's happened here? You actually decrease it. You can calculate it and see it's decreasing. Okay, so if you have a device, a startup, and see, oh damn, my capacitor is too high, oh, my capacitor is too small, I can just change it, right? It can add stuff and throw away stuff. Perfect. So this ends up to be, I'm here, to be this one, C1, C2, 3, 4, 5, and C6. And these all three connect in series. Perfect. So we know the formula. So C total, now I'm allowed to say it, for state 1 of the pedal board, of the effect, the guitar effect, is this, and this equal to taking the 1/, of each one of them, and you're going to see usually in the homework and exercise, this is a simple numbers that you just need to put inside and calculate it. Perfect? You got it? Okay. And I want to give you an example. You're going to see why I say it, but I think about capacitor as a spring. Okay? That's the way I see it. What do I mean? If you can look at this thing, this is kind of a spring, right? I can change its, I can deflect it, you see it? I can change. So this is like two capacitors in series. And this sorry, okay, I'm going to explain it to you later, okay? So let's do our next question, which is to find C total, but right now, not for state 1, but for state 2, okay? So help me to draw the new circuit that we have. If right now we connect not to here, but to here. Okay? Got it? This one connects to here. Okay? So we have first C1, and then we have, wow, this is really not working. We have another one. This one. Perfect. Bye-bye. Okay, so right now we have C1, and after that we have junction. We have, help me, what do we have? Which capacitor? C2, great. And then after C2, what do I have? In junction, going out or going to C4? Okay, so going out or going to, let's draw it in this way. I'm going to C4. After C4, what I have here? A tricky question. This is not a junction. This is not an option anymore. No current going to go in that direction. This is only to C5 and C3. So here we have C5 and C3, and let me do it nicely. Okay. So this is our new circuit. Got it? So we can found more really easily this thing, right? This is gonna be called C3, 4, 5 to remember. And the way to calculate them in series, it's sum 1 over Ci minus 1, and this is equal to 1 over C3 plus 1 over C4 plus 1 over C5, right? And you're going to have a new circuit, really easy circuit, which is C1. We have here C2, and we have here C3, 4, 5, right? This one I can calculate using this expression, right? Just sum them up, no worries. 2, 3, 4, 5, just equal to 3, 4, 5 plus C2, right? And then we have only two capacitors in series, so we killed it, right? We're gonna have this configuration. C 2, 3, 5, and it's gonna be equal to C total of state 2 of the guitar effect, gonna be 1 over C1 plus 1 over C2, 3, 4, 5 to the minus 1. Okay, so you can ask yourself, okay, wait a minute, why should I have so many capacitors and not just have two equivalent capacitors and choose between them, right? So usually you don't have only one button on the pedal board, you have many configurations. And guitar player can do, okay, let's enter with this sound to the solo. Let's do the rhythm part with that. Let's change this through the song. So we're gonna have many options. And if you have many capacitors and many ways to connect them, you're gonna have many interesting sounds. Okay, you got this idea? Perfect. So let's move to our next question, which actually happened to me today. What happened to me is that I didn't plug the phone properly this night, and when I wake up in the morning there was no alarm, right? So I wake up really strong and healthy, and wow, I slept really well. Why so? And I see that the alarm clock did not work because the battery for the phone for the next day, the day after. So what you can actually do in this situation, so Samsung and other company actually invented a new idea which calls super capacitors, which is super chargers. They can charge for 100% your battery in just a few seconds. So how cool is that? So let's do a question about that. So this is our next question. I'm going to clean this. So sorry guitar, but we finish with you. Okay, so the next question is just going to be about supercapacitors, super capacitors. And the first question I want to do is kind of a warm-up, is what is the electric field from an infinite plate? Okay, let's say with positive charge. Okay, what is the electric field? What?
2 pi kc.
Okay, but with the epsilon, we can use Gauss's law, right? Just to remind you, what is the electric field of an infinite plate charge? Okay, so what we're going to do, we're going to use Gauss's law, right? We're going to do some shape around it. We know because of symmetry that all the electric field is pointing in this direction, right? So all the contribution, let's do it like this. Gauss's law said EdA, right, dot equal to Q in A divided by epsilon naught, right? So we're going to choose this area, random cylinder, for example. We know that the charge inside is only the one touching the plate, right? This is the only charge inside, so if we know sigma, it's sigma pi r squared, right? And all the electric field that actually counting is only this, right? Only the one on the top and the bottom, so we actually have here 2 pi r squared multiplied by the height above the plate, right? And pi r squared cancelled out, and we know that the electric field above an infinite plate is actually sigma divided by 2 epsilon 0. This is really important formula, okay? Infinite plate, electric field. Good, but capacitor is actually what? Is actually 2 plate, right? It's looking like this. One is going to be positive charge, and one is going to be negative charge. And if, for example, you are, let's say, Steve Jobs, want to do some capacitor, some phone charger, let's see if there's any radiation from the charger, some electric field. Okay, so the next question would be, what is E in the world right now? Okay, so how we can solve that? Which principle can help us? Exactly, superposition. If I know that this one produce electric field that going that way and that way, right? Which equal to sigma over 2 epsilon 0, right? I know that this one do the same thing but opposite direction, right? He suck in charge because it's negative. He sucks in charge. He wants the charge to himself. See it? And this is size of it gonna be the same, right? So this is the positive. It's the positive charge, right? So I wanted to see something really interesting about the capacitor. What is the electric field outside of the capacitors? Actually 0, they're canceling each other up, right? And also here. But what's going on inside the capacitor? It's doubled, exactly. It's not this, it's this and this, right? In the same direction. So this is a really important formula. So the electric field inside the capacitor is E equal to sigma divided by epsilon. Got it? In a capacitor, right? Inside. But what's really cool is outside it's 0. So it's not that dangerous to be near a capacitor, right? But I want to have some correction. What is the size of the plate? And in real life? It's not infinite, it's have a finite size, but this is a really good approximation. So if you're going to be far away from the plate, this thing going to cancel out. But if you're going to go close, the assumption would not be that perfect, okay? But that is the concept. Great. So what I want to ask you is, what is the charge on a capacitor? So let me draw a capacitor. So this is going to be our next question. What is the charge on a capacitor? And we have our charger. It's looking like this. We have here a plate, a battery, and here a plate. Okay? You see it? So to find out this thing, all you need to know is the famous equation for capacitance. When this is actually what's defined capacitance. Capacitance is actually telling us how much charge this device called capacitor can accumulate. Okay? And it's equal to C multiplied by V, which means how many energy you try to force on this stuff, okay, to gain some charge. This is the correction factor, C, okay, which depends on the geometry and other stuff. We're going to talk about that. And this is the charge you're going to have. Why this thing happens? If you're going to think about it, if I have here some voltage for the wall, for example, so electrons can move around, and they're going to accumulate on this part, going to be negatively charged. And here, what's the electron going to say when they're going to be here? Here there's negative charge, and here is electron with negative charge. They're going to say, fuck you, I'm leaving. I don't like you. There's a repulsion, right? So electron would actually leave this plate, and what's it going to leave behind? The proton, the heavy protons, right? That cannot move like the electron. And this one gonna stay without electrons, right? And this is going to be positively charged with Q, and this one would be negatively charged with all the electrons. Okay? So that's what you actually do in a capacitor. You actually separate charge. You put a lot of negative charge in this size and a lot of positive charge in this size. Okay? And C actually, this parameter, I want to give you the famous equation for C. C for a straight plate, just two plates that looking on each other like this, two plates. Okay, it's really an easy formula. Is C equal to the size of the plate, A, area, the material that you have inside, epsilon R, okay, and divided, let's call it epsilon node in the case of air, and divided by D, the distance between the plates. Okay, D, this is A, the area, right? And epsilon is actually the material that you have in between. For example, in air molecules, this need to be epsilon R, right? Multiply epsilon R, and in our case, epsilon R multiplied by epsilon 0. This is the formula actually. This is of epsilon R is 1 for a vacuum, but also for air. And mostly gases, it's going to be 1. Okay? It's going to be given to you what is epsilon R. What is the material that try to, you know, affect the material that between the capacitor, the non-conductive material. Okay? Perfect. So, my question to you is, what is the, okay, I'm going to tell you what's going on. Okay? During this, working with these capacitors, okay, there was not enough capacitance, okay, to this device. Okay, so how we can increase the capacitance? We can add to the picture another capacitor, right, in parallel, in series, and change it. But another concept, if you have a lot of devices, is just to plug in a conductor. Okay, so that's what we're going to do. So we have this circuit here. We have here our capacitor, first plate. This is the space that was between the capacitors, between the one capacitor, and I'm going to plug in a conductor. Here's the conductor, and I'm going to plug it in, okay, to this configuration. Let's do like this. This is the new configuration, and this is going to be dashed. That's what was in the past. That's what I did. I put it here. What's going to happen? What's going to happen to the charge? Let's think about it. From this side, you're going to have a lot of electrons that want to flow in that direction, right? Electrons, they're going to fly to that direction and accumulate here. You see it? It's going to be negative. What's going to happen to this face? Electron going to leave to that side and going to left this place positive, right? And what's going to happen here? Electron would say, I don't like this. I feel a repulsion. They're going to leave, right? And put behind positively charged. So what we actually did, we built two new capacitors. You see it? This is a capacitor, and this is a capacitor. You see it? Good. So I want to ask you, what is the electric field in space in this configuration? So what is the electric field in space, right? So if we're going to draw it, let's just draw the electric field ourselves. So here, what is the direction of the electric field? From plus to minus, right? That's what we're going to have here. Yes? And here, the same thing. What is the electric field inside a conductor? 0. Okay, this is something from the lecture. In a conductor, perfect conductor, the electric field inside is always 0. It cannot accumulate any voltage. Okay? Good. So let's give an axis. Okay? So it's going to be easier to us to follow what are the heights. So this is going to be the z direction. This was the originally distance between the plates. The original distance between the plates. So this is going to be called d, right? This is our first height. So this is going to be d1. This is going to be d2, and we can actually call for simplicity to this distance L. This is the length, the thickness of the conductor that we put inside. It's clear? And if you want to write it mathematically, E as function of Z is equal to what? When we are talking about Z's that actually smaller, Z that actually higher than D, then D2, but not exceeding outside of the capacitor. So we have this electric field, which is sigma over epsilon, right? In what direction? Minus Z direction. Inside the conductor, D1 and D2, we have electric field of 0. Why we have inside a conductor electric field 0? What is a conductor? Conductor is a material. The charge can go around the conductor freely. That's the idea of a conductor. The charge can just move whatever they want. If there is electric field, the charge would move according to the electric field and cancel it out, right? If I have here some positive stuff, all the negatives would follow up, and far away, positive plus negative, 0, right? So electric field inside a conductor is always 0, okay? And if you want to really go deep into this thing, if you look at really small time scales, it's not correct. But it's taking a really short time for that to happen. And in this class, we're going to always say 0. And the last part that we have is between D1 and 0, right? And we have the same here, right? Got it? This is the electric field in space, and of course outside of the capacitance, if we take the assumption that the plate is really big, it's 0 outside. Yes?
Why negative?
Why negative? This is the Z direction. Okay, so this is the negative sign. Great, okay. So another thing that I want to say is when we enter this conductor, a short time before, I open this circuit, okay? Which means I charge this capacitor, these two, okay? I open this. When I open this, what's happened to all these electrons? They stuck. They stuck here, which means here we're going to have some Q. And this Q, the charge accumulate here, would not change because it's stuck. Got it? Right? And this one would not want to leave because this one actually holding them. You understand? Okay, the electron would not want to come back because this electron actually here repel them. Perfect. So if you see question that somebody open this, it means the charge stayed the same. Okay? And if you have a question that it's connected, it means the voltage stayed all the time the same. So in this configuration, what's going to change? The voltage going to change. Perfect. So I want to ask you right now, what is the new capacitance of this configuration? Okay? So I'm going to go to here. So we can draw really easily our circuit. It's looking like this, right? Hop, 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 right? What is this? This part. This is the first plate, the lower plate. This is the upper plate. This is the conductor. Okay, this is this I in our ideal circuit. It's actually the conductor. Okay? Perfect. Note, this line is also a conductor. It's the wire of the circuit. It's just a conductor. Perfect. So what is C total of this configuration? They are connected in which way? Series, exactly. So I know the formula. The formula is 1 over C1 plus 1 over C2. And I call this to be C1 and this to be C2. Right? This is the formula. And we know this term, right? This term is, I gave you the formula, this, right? I'm going to write it again. It's C equal to A epsilon divided by D, okay? Note that if the area is big, there's a lot of place for electron to accumulate, to have fun, to have a party, right? And if this is really far away, the plates would not talk to each other, right? If this is far away, this is decreasing. And the material is also important. In our case, and most of the cases, here they're going to be just a vacuum. I'm going to send you another question, which is going to deal with the oil. Okay? And then you have here something. Okay? So I need, but the flip one, right? So this is D over A1, D1, epsilon node plus D2, A2, epsilon node, right? Divided by minus 1. Not divided to the power of minus 1. So the area of the capacitors and the conductor was the same. A1 equal to A2 equal to A. So I can write D1 plus D2 divided by A. And this is to the minus 1, right? And perfect. And I didn't write what is D1 and D2, right? Sorry. I write here D1 and D2, and this is not correct because we declare different distances for them, right? We said, okay, for the first one it was okay. This was D1. But for the second one, it's actually D minus D2. You see it? I'm going to go here to the board. Cameraman, can you see us? So this is the distance of these two, and this is the distance of these two, which means D minus D2. Got it? So that's what we have here actually is D plus D1 plus D minus D2. What is this? D1 minus D2 is actually minus L, the length, the thickness of the conductor, right? So this ends up to be A, I also going to flip it with the minus 1, divided by D minus L. So this is the new capacitance. If you put a conductor inside, boom, we got that capacitance. Okay, so now I want us to find what is the voltage, let's do it here. What is the voltage that we have after putting the conductor inside. Because we explained that charge cannot change, but voltage can change, right? So, and let's use the definition. This is going to be the change in potential, right, between the upper part, this is Z equal to D, and this is the lower part, Z equal to 0, right? What is the definition of changing in potential? Is minus, this is rehearsal of what we had previously, before the vacation, right? Dot dz, right? This is the direction we're going to, this is the electric field that we have, and we know electric field everywhere, and we go the direction from 0 to D, which is the potential on the capacitors. And we need to see that the electric field is actually changing, right? We have in the middle the conductor, the electric field there is 0. So we actually need to split this integral. Be careful with the minuses. This is the electric field inside, right? This is the capacitor. This is inside the conductor, right? D1 till D2. And this is outside the conductor to the second capacitor, which gonna have QA epsilon, right? DZ. So this one is not of our interest, and this change in potential, we can write it as V final, the voltage that we have in the end of the procedure, right? So we're gonna end up with, if you're gonna rearrange it, we're gonna have D1 multiplied by that, D2, D minus D2 multiplied by that, right? And we're gonna have V final equal to Q, D minus L divided by A epsilon naught. And I did the same trick. I saw D1 minus D2 and I said it's minus L. Okay, and this is V final. And what I want to tell you right now is that I taught you a really important formula that we didn't use. I taught you this concept, right? Q equal to CV. And this is really important formula, okay? So I like, if you want to remember it by heart, I think about that Q actually applying for a job and sending his CV. Okay, this is my stupid method, but it's working for me in the exam. So immediately I see the equation, I understand what I'm missing. Okay, so what I want to tell you is, we know C final, right? We just found it previously, is to sum up the capacitance, right? The sum up the 1 over the capacitance and then flip it again, right? We found it. What it was? It was A epsilon naught divided by D minus L. And we know that the charge did not change, right? Qi was equal to Q final. This is not changed during the process, right? So what we can say about the voltage? We could just take Q divided by that and have voltage of the final. We just did that, but this was a stupid step to do, okay? Because this formula actually gives you it immediately. You see that this is the same formula, I just need to rearrange it, right? To put C here and VF there, right? So what I wanted to see is always using this equation and ask yourself if it's working for you or not, okay? Perfect. Now I want to talk a little bit about energy. Is this idea of putting a conductor instead of bringing a new capacitor would be helpful, will be actually a good idea in the when you think about energy. So let's ask how much energy this actually cost me to bring this conductor into the game. Okay? So this is the work I've been doing. Work is actually change in energy. And we don't do E as energy in physics 2 because we have electric field, right? So we do actually U. And we have two states, before the conductor and after the conductor, right? So we have actually U final minus U initial. Two steps. And I'm going to draw something, okay? but I want you to see it. This is the energy that you have from a capacitor. And I want you to tell me what it resembles, okay? What it, if this is familiar to you from Physics 1, heads up, not kinetic energy. We're talking about potential, okay? So, half in the beginning, C here, and V here. This reassemble for you something? Recognize what this look like? Spring, exactly. This is look like a spring. And I'm thinking about the capacitors as springs. Instead of C is how much I resist to change, right? And instead of V, how much did you try to pull me? This actually tells you how much energy you have in the spring, right? Good. So we actually need to calculate. So this is the method for me to remember it. Okay? And now we want to calculate U for each state, I and final. Okay? So let's do that. So U initial is really easy, right? It's going to be really fast. We're going to say, okay, U initial is half C that we had at the beginning, right? Ci, which is A epsilon divided by D, the big D, all the distance. And the voltage was the voltage of the battery, right? The given one. That's it. We have it. 2 V0 square. We find Ui, and the big challenge is actually finding UF. So what is UF equal to? So instead of using this formula, I can use this, Q equals CV, right? Q equals CV, right? I can rearrange it if I want, because what I do know, I know that Q stayed the same. So I can actually play a little bit, and I only do that because I want you to see how I can manipulate this equation to something else. Using that, I can say that V equal to what? To Q over C, right? Can plug it in, half C Q square divided by C square, C and C cancel out, and we can also use this term. It's also valid, right? This stay the same. I don't care if it's final or initial, right? But C changes. C equal to what we found, C final Q square. And if we're going to plug in everything we know, we're going to get C is, this is A epsilon divided D minus L, right? And here we know what is Q. It's just the previous C that we have before multiplied by voltage, is this. C that we have before multiplied by voltage of the battery. So here we have C, A epsilon node D multiplied by V, and don't forget to put it square. So this is the term. We're going to rearrange it and clean everything, right? Rearrange it and clean everything. We're going to get this term. We're going to get U final equal to V square A epsilon node 2D 1 minus LD. And now I can actually calculate what is the work. What is the change between final and initial. Just take the final, subtract the initial, and what we're going to have, if we're going to calculate it, we're going to have L, V square positive, A positive, epsilon positive, 2D positive, but outside you're going to have a negative sign. You see it? What does it mean that we have a negative sign? This is not cost me money, it's not 100 joules, it's not 0, it's negative. This thing want to happen, which means if I'm going to come with my conductor next to the capacitor, I'm going to get close and close to the capacitor. In some point, this negatively thing would going to suck it from me and take it away. It's going to suck in the conductor. It's not free, it's actually going to help you doing that. You understand the concept? So this is really genius. You can just bring a plate, not another capacitor, and that's going to be enough. By the way, I brought here some capacitors that you can see. Here you have a circular plate, okay? That's how it looks like. And in between they put some material. And you can also have and look about this capacitor, this kind of thing, which is two plates that, like a sandwich, was rolled up. And they give you this configuration, okay? Two different plates. And there's many plates. And what's really cool about this guitar, that maybe I can show it to you, that they love to talk about how good the capacitor that they have. They do that transparent. So you can see, wow, we have a good capacitors inside. You should buy this guitar. So this is the concept here, why this is transparent. Okay? So this was the tutorial about capacitors. And I'm going to send you more videos about other kinds of capacitor. For example, a cylinder capacitor, a spherical capacitor. And this is mostly the capacitor that you're going to encounter in the class. Okay? And that's it for today. Thank you for being here. And next we're going to talk next week, not about the capacitor that can actually accumulate energy. We're going to talk about the other guy, the one that wants to spend it all, to use the energy, to make light, to make heat, to make sound. This is the resistor. Okay? So we're going to talk about that next week. Thank you very much. See you next time. Go ahead.
Why, when you're saying Q squared, why don't you use L?
What?
Like, why do you say only D and not D minus L?
D minus L.
When you're substituting for Q.
Q, because this is the first Q, the initial one. Oh. The initial one was C multiplied by V. Right? This is the original C.
Okay.
I use the formula Q equals CV. Q applying for a job.
Oh, but if it's initial, oh, here it doesn't apply that initial is the same as final?
What? Q is the same initial as final. Yeah? So I change it to Q to actually use this multiplication. C initial multiplied by V initial.
Yeah, but you need a...
That's what I did here. C initial multiplied by V initial is actually Q final or initial. I don't care. They are equal to each other.
Oh,
got it?
yeah.
Okay, perfect.